Hi folks, we're continuing our discussion of design capacity and available pressure with the situation where you might have to make a calculation of assumed flow because perhaps a project is just in the planning stages and you don't have information about what the water supply situation might be, but you still need to calculate the amount of water you're going to need for your irrigation project. So assumed flow, again, is the calculation of a design capacity for a project where there's no existing water service. And it utilizes this calculation of gallons per minute with this constant of 0.0104, which just gets you to the units of gallons per minute. Reference ET, area of the project, crop coefficient of the plant material, distribution uniformity of the irrigation system, and the hours available for irrigation. And you may wonder if there's a worksheet to use for determining assumed flow like we did with metered municipal systems. And the answer is yes, and we're going to work through an example using the worksheet that I have open up over here. So the first thing that I want to point out about this worksheet though is that it's a little bit different from the last one we worked with in that while you do have a lot of the same information included on this front page, which is titled Total Assumed Flow, you also have several other worksheets behind that allow you to enter information for individual hydrozones. So what you see here is some of the information that will be requested for those hydrozones. And we're going to go through an example of a park, and we're going to come over here to our worksheet and go to hydrozone 1 to get that started. And that's what you can see here. Oh, I want to clear this and show you how I enter it. Okay, so with our example, we've got 115,000 square feet of turf, reference ET of 0.15 inches per day, Kentucky bluegrass coefficient of 0.8 or 80%, distribution uniformity of 60%, hours available for irrigation of 6. We have some other information including where the point of connection is, how high the highest head is above that point of connection, water pressure from the city main, the location of the city main, and also some additional information about the service line that we will use as we go back to the total assumed flow worksheet. But to begin with, we're going to use this hydrozone 1 sheet and we're going to fill in as much information as we can. Line 1 asks for the reference ET for the project site, and it tells you that that's typically between 0.15 and 0.35 inches per day. Now you can also click on this particular cell, it's called typical ET rates, and that allows you to look at a range of ET rates for climate situations ranging from cool, humid to hot, dry. I didn't say so in the example, but we're considering this as a cool, dry climate, so we're going to use a reference ET of 0.15. So I'm just going to hit 0.15, enter. Okay, and it moves down to the next cell, which is area. The area given to us is 115,000 square feet. So I'm going to enter 115,000, no comma, and enter. And the units are already over here, so you don't have to worry about that. Crop coefficient is listed here. It tells you what they are for Bermuda grass and bluegrass. So I'm going to hit 80 here. But if you didn't happen to know that, again, it gives you some information here. Typical crop coefficients. So it tells you what they are for native plants, warm season grasses, trees, and so on. Okay. Back to line 4, though, that asks for distribution uniformity, which was given to us as 60%. So you don't have to enter the percent, just enter 60 and then hit enter. And then finally, line 5 is the hours available for irrigation each day, and that was given to us as 6. Okay. Now notice what the worksheet has done is calculated an assumed flow. So if we go back over here, that assumed flow, we had this formula to work with. The numbers were filled in like this, 0.0104. It used 0.15, which we entered for reference ET. It used 115,000 square feet, which was given to us. 0.8 for reference, crop coefficient, 0.6 for DU, and 6 hours available, and we end up with this 39.9 gallon per minute assumed flow. Now let's go back to our worksheet. We filled out all we could about our hydrozone. I'm going to go back to the front and notice that it's pulled that information for hydrozone 1 and entered it here. We haven't done anything else with these other hydrozones. There are space to add up to 8. So it's just taken what we do have, which is hydrozone 1, and we have a total assumed flow of 39.9. Now, there is certainly some other information that we can enter, and lines 10 through 13 have to do with the static pressure of our water source and what elevation change effects there may be. So if we go over to the worksheet and click on that cell, line 10 asks for static pressure at the source. We go back to our example, that is 85 psi. So in the worksheet, I'm going to put 85 psi, enter. Net elevation change of the water source to the point of connection. Now let's go back over here to our example and let me show you a couple things. So what you need to make note of is that you are told the point of connection is at the meter. You are also told that the city water main will be 4 feet below the water meter. So here in line 11, where it's asking you for the net elevation change from the source to the point of connection, it's going to be 4 feet because the main is 4 feet below the meter, the point of connection is at the meter. So you go back to your worksheet, you enter 4, hit enter, and it goes ahead and calculates your PSI change due to elevation change. Now there's some information that can be added about in lines 14 through 16 about the service line, okay? And you did get some information about that as well in the example. So let's go back to our example. The main piece of information that you have here is that the service line is type K copper and it's 45 feet long. Okay, so service line, we calculate that here. It comes up with a drop-down menu. I'm going to say it's type K copper. It automatically does some calculations. In fact, that's the beauty of this worksheet. It helps you to size the service line because, again, in assumed flow situations, you don't really have a water source yet. And it also sized the water meter. So that was good. All right, now the next pieces of information that we want to look at are in lines 17 through 24, and we'll again be adding a little bit of information, not a ton. But it asks for the service line estimated length. It asks for it actually gives you a pressure loss per 100 feet, which comes from a friction loss chart based on what we set up here about the type K copper. And also gives you the opportunity to enter information about any isolation valves or other valves that may be put on the system and what those pressure losses may be. So we already said what the service line was going to be. And let me just go back and double check. 45 feet long. So that's a piece of information that we can enter here. So service line estimated length. We're going to come up here to this cell. We're going to say 45, enter. And what it does then is it uses the information about the length of that service line, the material, type K copper, and the size to determine a PSI loss. And it does that calculation for you here. And it also determines a pressure loss through the meter based on the size of meter that was determined up here. And we didn't have any other isolation valves or other sources of pressure loss to consider, so there's nothing here. So what is happening in this section of the worksheet is it adds what we do have, which is pressure loss through the service line and meter, and you end up with a total pressure loss of 6.14 and an approximate dynamic pressure at the assumed flow that we calculated up here of 77.13 psi at the point of connection. Now we're not quite finished yet. In the last section, we estimate the pressure available at the worst case head. So that's very similar to what we did with design with the metered municipal system. So here, line 25 is a 2/3 estimate. It assumes 1/3 loss of PSI between the point of connection and the worst case head. Right now, that has determined that it's 51.68 PSI. So it took this line 24, multiplied it by 2/3, and ended up with 51.68 PSI. However, we have some additional information that we can use. So line 26 asks for pressure change from elevation change to that highest head. So let's go back to our example and note that it told us highest head is 22 feet above point of connection. So if we go back to our worksheet and we enter right here 22 feet, which is given to us, it adds that pressure loss due to elevation, or subtracts it, I should say, because it's higher than the point of connection, and we end up with an estimated dynamic pressure at the worst case head of 42.15 psi. So down at the bottom of this total assumed flow worksheet, you would have all of that information. So very similar to metered municipal, to the metered municipal worksheet, with the added utility of adding hydrozone information. All right, so to sum it up, using this worksheet, you're going to be able to determine the required design capacity, or assumed flow, and the pressure available for sprinkler operation. And this is a method that you can use when you have not determined what your water source is going to be. One example would be where there's a municipal system where the design is being developed prior to the installation of site utilities. So that is the end of the discussion of assumed flow. We will continue in the next lecture.